Hi, yeah.
And yes, and so his talk is going to be about revisiting alphabet reductions in Dinor's PCP.
Yeah.
We saw your screen previously.
Yeah. Unfortunately, there's some miscommunication and I don't have the slides yet. Maybe I will quickly explain. Sorry for the miscommunication.
You don't have,
The other
so
author
you're
is supposed
to
present, but
you're waiting
unfortunately
for
he's not
someone to
available.
send the slides to you, or?
Yeah, but unfortunately we couldn't make it. I'll quickly explain it maybe, or give the details.
Or do you think, because we could also change the order of the talks, and then if you expect the...
Yeah, I think the other author is, I think it's not available.
You don't think you will get the slides?
Yeah.
So, okay.
Yeah,
I mean, if you think you can
so.
explain
since it's
the result, there should also be a function of having a whiteboard or something, I believe.
Yeah, I could do that.
If you could do that. Okay, yes, perfect.
Yeah, so this result is about alphabet reduction in Dinor's PCP. So PCP theorem is about approximating max 3 set. So max 3 set is hard to approximate within this is the standard PCP theorem. And the way it does is by 2 steps: gap amplification and alphabet reduction. So it's traditionally we know that max 3 set is NP hard. That's the usual result. And to get this stronger result, we first start with a graph coloring instance and then amplify it to get a new CSP where the gap is large, but the alphabet also increases. And in the alphabet reduction, you have CSP instance I over large alphabet. And the goal is to come up with a new instance J over, let's say, binary alphabet. With preserving, not losing gaps so much. By that I mean, if in I, if I is satisfiable, J is satisfiable as well. And if I is, if we can only satisfy some 0.99 fraction of constraints in I, we can satisfy some, let's say 0.98 or some constant. It could be like 0.995, some constant depending on 0.99 fraction of constraints in J. This is the whole alphabet reduction step. And traditionally this has been, so this step predates gap amplification. And gap amplification is the main, like the new result in Dinor's part, but alphabet reduction, there's also previous paper which does alphabet reduction. Our result is that we achieve alphabet reduction in a much more direct fashion. So previously it was done using assignment testers, but we give a much more direct reduction. Our reduction is through the standard label cover long code framework. And our main observation is that the instance I that is obtained from Diner's amplification has rectangular constraints. Rectangular constraints are, let's say if you have two variables and a domain, these are the elements of the domain. If we draw lines which are satisfying assignments of the constraints, they are of the form union AI cross BI. So they are unions of rectangles. So traditionally, if you have label cover or something, they are projections, but these are weaker restrictions of it. And so we claim that once you have rectangular constraint, it's sufficient to use label cover framework. And this is our key observation, the first part. And the second part is to use predicate of our own choice. So we use a 4RE predicate, which is Hastad used in coloring hardness results. And essentially using these two steps, we prove that you can get alphabet reduction pretty directly without using assignment testers. And the reduction is the same label cover long code reduction that most of the previous results have also used, where you have a set of a constraint satisfaction problem over large alphabet. You replace them with a new variables with long code of variables in each block, and then add constraints according to the dictatorship test. That's our whole. It's basically a combination of two ideas. One, you just prove that the instance has rectangular constraints, which seems to be pretty simple observation, but for some reason it has not been used before. And the second is, since you are only aiming for TCP theorem, you are not aiming to prove hardness of a particular predicate. So you can use any predicate, and the predicate that we use makes the Fourier analysis very direct. So, and coming to questions, the biggest question is, again, maybe if you could try to simplify the gap amplification as well, but that seems fairly difficult. We did try for some time about it using these ideas, but that seems like fundamentally then some new ideas are needed to use these kind of like ideas to simplify it. That's it.
Okay, thanks.
Yeah, thanks, and yeah, again, sorry for the miscommunication. Yeah, let me know if you have any questions.
Yeah, if there are any questions, please speak up.
So Sandeep, I had a question.
Yeah.
Isn't every edge like a trivial rectangle? So what's happening with the rectangle constraints?
So let me put. Oh, I see what you mean.
So if the AIs and BIs are single vertex things, and then every edge is and then I can take the union of the edges.
Okay, let me clarify. The AIs are disjoint.
Oh, okay. Okay, good.
Thanks for the yeah. So in the projections, that's true, right? AIs are disjoint as well. Like if you just have constraints of this form, but here it's of.
Got it.
Yeah. Thanks for the observing. Yeah.
Okay, great. Thanks. Are there any more questions? Maybe one more. Anyone has a? Okay, if not, then thanks again. And let's move on to the next talk given by Eden. And he is going to talk about how to cut a ball without separating. Please go ahead.
Okay, thank you. Share my screen. Oh, wait, sorry. I still see.
Looks good.
Yeah, so I was just still seeing the participant list. Okay. Okay, thank you for coming to my talk. So this is joint work with Peter Kollmann from Charles University. And the problem I'm going to talk about, I'll jump right in. This is the L-bounded cut problem. So let me define it for you. So in this problem, we're given a graph. We're given two terminal nodes and some integer L, which can be part of the input or not. And the goal here is to find a minimum cardinality set of edges that cut all paths from S to T of length at most L. So this is a set of edges, which if we remove, causes the distance from S to T to be strictly greater than L. So let's see an example. Let's think of 4 bounded cuts, so L equals 4. And let's look at this graph. Okay, so if we wanted to completely separate S and T, that would be a classical min cut. We would have to pay k plus 1 edges in this instance. But if we're happy to cut just to ensure that the distance is strictly greater than 4, or that we cut all paths of length at most 4, then it suffices, for example, to cut just these 2 blue edges. Okay, so there can be a very drastic difference between actually separating and just cutting a bounded length paths. Okay, so what do we know about this problem? Well, we know that it's APX hard. We know that assuming the unique games conjecture, it's hard to approximate to within any constant. And digging a little bit deeper, more specifically, we know that for any value of L, there's an omega of square root L hardness, which is due to leak. Okay, so where does this hardness start? At L equals 3, the problem is still easy, but the best algorithms up until now for L, which is at least 4, were a ceiling of L over 2 approximation. And in fact, the APX hardness already starts for L equals 4. And both of these results due to Bayer et al. And also the unique games hardness of 4 over 3, that's the hardness of improving over or getting an approximation better than 4 over 3, also starts at L equals 4. This was not explicitly mentioned in the Bayer et al. Paper, but we observed that this follows from their reduction. Okay, so that's what we know, that's what we had so far. What are our results? So again, the only approximations for bounded values of L up until now were ceiling of L over 2. Okay, so here are those values. So first of all, we improved the approximation for 4 bounded cut from 2 approximation down to 4/3. And I'll remind you that this is optimal. This is the best possible approximation, assuming the unique games conjecture. For 5 bounded cut, we improved 3 down to 1.75. And for 6, we improved the 3 approximation down to 2.4. And actually for L equals 6, this is part of our algorithm for general values of L, which always gives an approximation which is strictly less than L over 2. So for any value of L, we beat the previous best known approximation of ceiling of L over 2, but we're not doing asymptotically better, right? So even this new algorithm still asymptotically behaves like L over 2, and you could be forgiven for thinking at this point that maybe that's where the hardness should be. But in fact, we show that's not the case, that you can actually get this asymptotically down to roughly 0.44. Okay, so there are 4 results here, and each one has different ideas. I thought instead of giving a high-level overview of everything, I'll just give you a quick glimpse of our 4/3 approximation for 4 bounded cut. Okay, so that's what I'm going to talk about for the rest of the talk. Okay, so what's our idea? For all the algorithms, our idea is to do LP rounding and we use basically the first LP relaxation you would think of, right? It's the natural relaxation with the constraint saying any path from S to T of length at most L should have at least one edge that's cut. And specifically for L equals 4, for 4-bounded cut. So let's first see a simple idea for rounding this LP, which is not going to work. Here on the right, you have the LP for 4-bounded, the relaxation for 4-bounded cut. So first, the idea would be take every edge in the graph and map it to some interval of length corresponding to its LP value, and then sample some value uniformly at random between 0 and 1, and cut every edge whose interval contains this value. So, right, this would be a great algorithm. This is what you do, or can do, for example, for the first coordinated cut, to get an exact algorithm. But the problem here is that there's no clear notion of what the right interval should be. And sometimes, clearly, there isn't a good notion of what the right intervals should be. So just to illustrate that, let's look at this simple example. And here's an LP, a feasible LP solution. And you can watch the recording later and check feasibility if you want. But the point is that this middle edge UV, it can be mapped in two very natural ways to an interval. So either think of UV as the second edge in a short path from S to T, in which case the natural mapping would be to map the interval, the edge UV to the interval ½ Or you could also think of a short path from S to T in which it's the second to last edge, in which case the natural mapping would be to map it to the interval 0½ So both of these would be natural mappings, and neither of them capture all the possible paths in which you would want to cut UV. Okay, so what do? Well, we resign ourselves to the notion that we'll have to map edges to, for this case, to two different intervals. And right, so the idea is you map E to two different intervals, one for paths in which it's the second edge, and one interval for paths in which it's the second to last edge. And then once again, we take this uniformly random radius between 0 and 1, and we cut every edge whose intervals are hit by this radius. And we can either hit one of the intervals or both, it doesn't matter. Either way, we cut that edge. Okay, so that's at least part of our algorithm, but this only gives a 2 approximation, right? Because these two intervals could be disjoint, and then right, we cut it whenever R falls in the domain of or range of total length twice the LP value. So we already knew that there was a 2 approximation, and I promised you 4/3. So we will run this algorithm, but we can only do this with probability 2/3. And that will get the probability bound down to where we want it. But of course, that's not an algorithm because we still have to do something with the remaining 1/3 probability. So with this remaining probability, we'll return a different cut. This cut will be based on cutting 2 radii, which are correlated rather than 1. And then we cut an edge according to one of 2 criteria. So the first criterion is if both the intervals corresponding to this edge contain one of the radii. So here's an example of that. R1 is contained in both of the intervals corresponding to E. And then the other criterion is if one of the intervals contains both of the radii. So here's an example of that where one of the intervals contains both R1 and R2. And so it might be clear to you if you think about it for a minute why the first cut really is a feasible 4-bounded cut and really cuts paths of length at most 4, but it certainly should not be immediately clear why the second cut has that property. And I'm not going to talk about it, but I did talk about it in the longer version of the talk. So if you want to know why this gives a feasible solution, you can watch that. I will talk briefly about the approximation guarantee. So why this is a 4/3 approximation. And I'm only going to talk about edges which have LP value, which is strictly less than half. The other case is quite a bit more technical, and you can read about it in our paper, as well as several other results. And in this case, just note that this last criterion can't happen, right? We can't have an interval of length strictly greater than half that contains two radii that are distance half apart. So we're just going to ignore that part of the algorithm and very quickly analyze what the probability is of cutting any given edge. So in the first cut, that probability corresponds to the union of these two intervals, right? So it's the probability if we return this first cut of cutting E is exactly the length of this union. And the interesting region in the second cut is the intersection of the two intervals, but then this intersection needs to be hit by radii which are sampled uniformly within intervals of length half. So rather than the probability being the length of the intersection, it's twice the length of the intersection. Okay, and then you just do a very simple calculation, right? It's 2/3 times the probability of being cut in the first cut, plus 1/3 times the probability of being cut in the second cut. And then overall, you get 2/3 times the sum of the lengths of intervals. Both of these are intervals of length xe, so you get the bound that we wanted. You get 4/3 times the LP value. Okay, so that's just a quick glimpse of snippet from our one of our algorithms. I'll just talk for a minute about open problems. So we've resolved basically 4 bounded cut if you believe the unique games conjecture, and if you don't believe the unique games conjecture, then probably you have more interesting things to work on than 4 bounded cut. But for any distance bound at least 5, this is still open, getting tight approximations or tight hardness or even tight integrality gaps or flow cut gaps. And there's also this variant in which you cut the nodes rather than the edges. We talk about it extensively in the paper. The edge version, which I talked about here, might be easier. It isn't for L = 4, but we don't know in general. It could be. And also there's the undirected version, which also has the potential of being easier, and we don't know, so that's open. And then you can also think about the case where L is part of the input, so it's not a bounded constant. And it would be nice to get any improvement over the current best algorithm or algorithms. Right now, the best approximation is O of n to the 2/3, n is the number of vertices. And also there's this node cut variant where it's square root n. And we don't, right, we still don't know anything better than that. And any improvement in hardness also for this general case. We don't have any better hardness that we know for this case than we have for bounded L, right? It's still APX hardness or no constant, assuming the unique games conjecture. So any of these I think would be very interesting problems to think about. Okay, that's all I have. Thank you very much.
Thank you, Eden. Yeah, I think in the interest of time, maybe we'll move on to the next speaker, who is Ojas. If you could share your screen and also unmute yourself. And yes, he's going to talk about an approximation algorithm for the max2 local Hamiltonian problem. Please go ahead.
Okay. So what I want to tell you all about, is really a body of work where there are very natural quantum generalizations of Csps, and people have only recently begun approximating them. And moreover, the approximations are purely classical. So it's a completely new area to mine kind of interesting approximation problems that have relevance to physics and quantum information. So let me just start by explaining kind of the generalization of max cut, in this kind of setting. So we've got the standard formulation for max cut. We have a relaxation. And what's interesting is that you can get sort of hard versions of max cut by now looking at the relaxation, and instead of having the vectors live in dimension n or unspecified dimension, we fix the dimension of the vectors that we want. So now, if this parameter is 1, we get max cut, but you could look at sort of other values of that. And this problem was first considered by Briette, D'Olivero, Filot, and Valentin. And they get a 0.95 approximation for this 3-dimensional case. And these approximations get better as the dimension increases. Now, the interesting part in the connection to quantum here is that these solutions end up being feasible for a quantum generalization of max cut. However, in the quantum case, there are other kinds of solutions that aren't feasible for this. And so with respect to that problem, We recently gave a 0.498 approximation in the last APPROX, in fact. You know, in max cut, things are pretty simple in the quantum version of max cut. And really, you could just think of it as you have a different objective where you have a coefficient of 3 here instead of 1. And that's really it. You know, that captures kind of the quantum approximation. However, things get more complicated for CSPs. So in fact, we can already start looking at a generalization of this rank 3 max cut, where now instead of taking the inner product, I actually give you a 3 by 3 matrix, and I'm interested in this bilinear form now on each edge. You know, this is actually pretty natural because this kind of bilinear form relates to the singular values of A. So, you know, I imagine this has applications maybe in machine learning and other kinds of things. But for approximation, this becomes more challenging. We can't treat, when we relax, we can no longer treat this inner product as kind of a single quantity. You know, now we kind of need to sort of vectorize components of these vectors themselves. Because A is a 3 by 3 matrix that's fixed, we can't just kind of generalize the dimension of these vectors. So if we go to CSP, things become more complicated. You know, we have linear terms, we can sort of add vectors for that. We may need to strengthen our relaxations. We can do the same thing on the quantum side. And this is the problem we consider. It's a quantum generalization of this. And again, you know, the real objective we're interested in will have special structure because the A's and B's are coming from a quantum problem. So another way of looking at so that kind of tells you what we're approximating, you know, the feasible solutions we're producing. But if you want some insight into what the quantum problem actually is, it's very nice in that nature is sort of constantly trying to optimize things. You know, you have a table, chair, desk, whatever, it's a physical system, and nature is trying to put it into some low energy state. And it turns out that that corresponds to an eigenvalue problem, kind of an exponentially large matrix, you know, in the number of particles that you have. I kind of give more context for the quantum stuff, introductory stuff in the full presentation. But the basic idea is that we want to think of CSPs, you know, classical and quantum, as max eigenvalue problems. And so in the classical case, what we can do is say you have an edge and you have a CSP on an edge, 2 variables here. What we'll do is we'll put sort of the CSP function, you know, of the values that we attain on the diagonal of a matrix. And now if you think this as an eigenvalue problem, you know, it's kind of trivial, but you will just pick sort of eigenvectors corresponding to the 2 places where you fully satisfy this function, and you know, you're in that linear. So what you can do now is you can say, well, instead of having a constraint where we have a diagonal matrix, make the constraint an arbitrary matrix. You know, there's some other structure on it to actually give us kind of generalizations of specific CSPs, but really this is the picture. And so now what happens is that your maximum eigenvector is no longer just kind of a classical string. You know, it's a vector in the space, but what ends up happening is that when we combine all the constraints, we sort of get an exponentially large matrix. And now your optimal solutions might have an exponential number of components, you know, in this eigenvector. And so you can about kind of approximating it with other sorts of models, and that's the idea. So these problems that I mentioned in the beginning, they kind of give you classical approximations, you know, kind of compact approximations to these potentially exponentially large eigenvectors. So for CSP, there's a very simple and natural way to generalize it. So you know, if we just have like a max 2 and constraint on a single edge, a defining characteristic is that there's just one way to satisfy it. And think of this as a rank 1 projector, you know, it's diagonal. So now we can say on each edge, I want to put down a general rank 1 projector that doesn't necessarily have to be diagonal. And that's it. You know, if we look at this, we get exponentially, now we're looking at the eigenvalues of this, eigenvectors of this. And you can still do randomized rounding. You know, there's a notion of kind of just random assignment that gives you the same thing. It gives you a quarter for the quantum case too. And that's what we're trying to beat here. So up to this work, you know, kind of the result was a quarter approximation for these problems. And just to make more explicit what I mean by combining this, so it's sort of the same thing that we do for CSPs. You know, if I give you a CSP on an edge and I have to extend it to kind of all n variables in my CSP, then you know, one way to think about it is now if I want the value on all n variables, I have 2 to the n values, and it's like tensoring this matrix with identity. And so this is sort of how we get the more general problem. You take these matrices I was showing in previous slides, you tensor with ID on all the other kinds of variables or qubits, and then you get these exponentially large matrices. They're no longer diagonal, and what we want are values and vectors for these. So as far as results go, as I mentioned, this is really new work, but the nice thing is that there's a kind of a nice one we can follow. You know, for many of the classes that care about in quantum, they're natural classical counterparts, and that gives sort of rise to natural rounding algorithms you might try. So, you know, in some of the early work from last year, for example, there's a natural generalization of kind of binary quadratic programming, and this kind, you can get this that you get kind of for the classical case. We look at sort of this positive two local Hamiltonian with generalization of max 2 and, you know, which captures max 2 as CSP, and we get this 0.328 approximation. So this result was kind of merged with results from Sean Hallgren. We were also co-authors on this work, and so these were kind of the first body of results beating random assignment. And then for max cut, you know, as mentioned, we actually get a 0.498. And the nice thing there is that 0.5 is actually the best possible if you insist on this type of approximation, if you insist on this class of kind of approximations to the max eigenvector. More recently, there's work that kind of is also a randomized classical algorithm, but it sort of gives a description of a quantum state. So this is where we eventually want to go, but it's really difficult to do this for more general problems. And so it's conjectured here that the right answer probably here is also 0.498. And in fact, the natural round algorithm, you know, numerically gives that to you, except we can't really use numerics as a guidance anymore. So this is one of the issues why it's very difficult to kind of approximate these algorithms, you know, approximate these problems using traditional methods. The rounding algorithms are very similar, but the analysis is much more complicated because, you know, this is for a single edge. Now we have sort of 15 parameters, you know, you have 15 parameters coming from your cost, and you have 15 coming from your SDP relaxation. The generalizations of kind of Lacerre hierarchy work here too, so that's nice. So numerically, you know, when you try and find out what the best sort of ratio you're getting is, the integrals that kind of looking at don't really converge too well, and so you know, you need other techniques, and we have some recent follow-on work that first time kind of introduces some of those, but there's still kind of you know, wide open questions here for almost any generalization you can think of. So for example, you know, there are probably unique games hardness results here. We haven't had time to engage those. So are there other techniques you can use for more general quantum CSPs? And in fact, you know, we're looking at CSPs because there's the notion of kind of generally approximating constrained problems really, you know, kind of unexplored. So things like set cover and all that, you know, no one really knows even how to come up with good formulations of those. So this is just sort of the first step. And then finally, you know, can we actually come up with quantum approximation algorithms to these problems? So this is all classical I've talked about, but an interesting question is if you actually insist on quantum approximation algorithms, can you get better ratios? So I'll leave it at that.
Okay, thanks a lot. Good. We're at 33 now, so maybe we'll end the session here. Of course, you know, everyone is welcome to stay a bit longer if you have some questions, but I will end the session with this. And let's thank all the speakers again. I will applaud for everyone, I guess, symbolically. And I think we'll reconvene in half an hour with the invited talk in this Zoom session, by the way. Yeah. Thanks.